In an earlier video, we discussed how systems might build themselves. And so here's a small structure with just 2 nodes and 1 edge. And then we showed how you could add a 3rd edge node and a 4th node. And that would be the first of the single surface triangular neighborhood networks. That single surface object is something like this. This is a pipe. Okay, we've seen balls and other such things, toruses. But let's just go back to the single edge here and ask, well, how could we re-represent this? So if the representation of the single edge is something like this in the rapid prototyping tool, my Knupffelis that I use, what could we do that would make a more complex system, or a system that is capable of more complexity? And so the idea that I had was that you could construct a surface like this, a pipe, that represents the behavior. You remember we discussed here at this level signals flowing back and forth on the single edge. So what's clear, of course, is that this pipe structure itself has structure like that. And this is represented in the Knupffelis as the edge in orange in the middle of the pipe, which happens to be in green here. But of course, this pipe has edges and nodes, and so if we represent each edge here by a pipe, then we have the beginning of recursion. So this is level 1 in the network. This is level 2 in the network. And this pipe here would be level 3 in the network. So that's what we want to do. We want to make a representation where you start out with first an edge, or a collection of edges making a single surface object. This is a single surface object. This is a single surface object. And then we'd like to be able to construct a representation that's more complex, that has multiple levels, where you would represent first the first level structure in orange by the second level structure, and then each edge of the second level structure itself by a pipe. So this is what we've done now. We've taken a tetrahedral triangular neighborhood network, first level, 1 level structure, and represented that structure by a second level structure. So this is a tetrahedron. Each edge is represented by an orange pipe. In this case, the pipe is a banded pipe with a circumference of 3 nodes. There are, as in the first level model, there are 6 such edges, and we can show each of them like this. But of course, each pipe is connected to a node, and the node is shown in blue, light blue. So just as the edge, which was just a simple line in the first level structure, in the second level structure, and the node was just a point where lines come together. In the second level structure, the node actually has triangular neighborhood structure all to itself. As I said, this is represented by the blue. So each node has considerably more structure. I mean, in this first level model, there are only 6 edges, and here I'd have to spend some time actually calculating how many edges are in this model. Of course, the pipes needn't be 3 circumference pipes, and they needn't just be 2 or 3 bands long. They could be as long as we want, okay, and they could be as big as we want. Of course, as you make the pipes longer, the nodes will be further away from each other, and as you make the pipe bigger, in this way, you're going to have bigger nodes to accept these bigger pipes. So, although there's a huge, probably on the order of 501, well, let's say there are 600 edges in this thing, I don't know. But so here we have 6 edges, and let's say we have 600 edges in this structure. So that's 100 to 1 expansion. If we change the length of the pipes, the numbers go up. If we change the circumference of the pipe, the numbers go up. And of course, as we do that for the circumference, then the size of the nodes will have to change. So we can, here we have 100 to 1 ratio between the first level model and the second level model. But of course, we could go to 1,000 to 1 by scaling or by lengthening and broadening the pipes. So any number of ways that we have for making larger structures, larger in the terms of this is a second level model, and the number of nodes and the number of edges can be increased as we wish in a certain sense. So that's one way that you can build a second level model. So as always, these things start out as just experiments that you're doing. And so I said to myself, well, if we have well, to go back then, this second level model was based on the 3 pipe here. And so I said, well, we have banded pipes and vertical pipes. So now could we construct a second level model using a banded pipe? And the answer to that, of course, is yes, we can. I should put a yellow or some other color green stripe here just to show that. In any case, what you see is that once again we have quite a number of nodes representing the edge. There are 6 such edges in the complete structure here. And now the nodes take on an entirely different character. So if you see this structure here and this structure here, there are more nodes in this structure using the banded pipes than there are in the model that has the vertical pipe. The nodes here are, in this case, more minimal. It's not clear how that will go as we scale. I mean, certainly we can scale this model, first of all, by putting a node in each triangle, which would be a scale 1. Of course, we can make the vertical pipe as long as we wish, and make it have as many elements in the pipe circumferentially as we wish. So, as with the other model, we can take this structure, make it much larger, either by scaling or by expanding the length or the circumference of the vertical pipe. So these are 2 models that represent 2 different ways of building second level models of triangular neighborhood networks. Of course, as we've mentioned, each of these edges here can be represented by a pipe itself, and that would produce a third level model. So if we got any of these initial models on the order of 100-to-1 expansion between the prototype here and either of these two models, then as we go to the third level model, we're going to get another at least, let's see, how do I think about this? 1,000-to-1 probably expansion as we go from this model to, is that true? I'm not sure about that. I built a second level model of the 6-edge node. It looks like this. The 5-edge nodes are in purple. The main body, including the pipes, are in red. The green elements show that this is a 3 circumference pipe. Each one of the pipes is 3 edges in circumference. When I built the model, it looked perfectly stable and symmetric, and when I play with it in this manner here, there's no particular problem with the strength of the model, one could argue. So this is a banded pipe as indicated by the green elements. I decided then I wanted to build, because for the 5-edge node, the second level model, there were 2 structures, parallel, the vertical pipe and the banded pipe. And so I wanted to build the same sort of model for the 6-edge nodes. This is a relatively big model. These are vertical pipes indicated by the green elements here. And these pipes are 8 edges in circumference. That was the only symmetry that I could find. 6 circumference vertical pipe doesn't have the symmetry for forming 6 such interactions of the pipes. So I was forced to use a bigger pipe, and this is the structure that resulted. What you see here is, since the 5-edge node has a 6 pipe as its pipe interface, and this model only allows an 8 pipe. The question was, could one convert an 8 pipe into a 6 pipe? And the answer is yes. If you put a 5-edge node here and a 7-edge node here, this has the effect of converting an 8 circumference pipe into a 6 circumference pipe. When I built the model, there's a certain weakness in the model. It's difficult to see here, but that is one of these psychological states that I get myself into occasionally. It just didn't seem as if the structure was as strong and as stable as it might be. So what I'm going to do next is to put a toroidal hole into this structure just to see what it is and what it does for the structure. So first I recorded the model without the toroidal hole, and now I'll put the toroidal hole into the model. I wanted to show the side view of the vertical pipe to show that how 8 circumference is reduced to a 6 circumference. That was not quite so clear from just the top view. This is the second level model for the banded pipe version of the 6-edge interaction at a node. As I mentioned before, what I've done now is I've put a toroidal hole in light blue. And this has the effect of stabilizing the model. I mean, this is now a glorious and stable structure. It's just wonderful. But what's very interesting, and in a later video we'll have a very long discussion about signal interaction at nodes in first level, second level models, whatever. But inasmuch as we'll also later show that the signals are really toroidal holes that are moving along the edges of a pipe, it's clear now that the effect of this toroidal hole is to create what I think of as a Chevy Chase circular. That is to say, at Chevy Chase, the interface between Maryland and the District of Columbia, there's a roundabout. And so here's a roundabout in some sense. So a signal coming in wouldn't necessarily go directly across. It would go around a roundabout. So that modifies my view of how signal interaction at nodes occurs. And so this is what's really very interesting, is that the first level model has no structure. It just has 6 edges coming together. And so when you think about, for example, signal interactions, you only have a simple view. But at a second level model, you now have structure, and the structure, in this case, the toroidal hole in the center, acts to divert the signal. Now, whether it diverts left or whether it diverts right, well, that's not quite so clear at the moment. But this single model has changed my view of what edges do as they come together at nodes. In the first level model, there's no structure. But in the second level model, there's structure, and the structure has new properties. And that's exactly what you want to have happen. And so, you know, the whole process of making these videos is just an exercise in trying to communicate. But the fact is that as I try to make the videos, the things that I have to do in order to make the video complete now introduce new properties into my thinking. And this is just an extraordinary behavior. And so, although that's the vertical pipe version, I immediately went back and started to put a toroidal hole, in this case a 3-hole, into the 6-edge node, second level, of the banded pipe version of the 6-edge node. And once again, the structure accepts the vertical the toroidal hole, and it just completes the model. I mean, it's just absolutely fantastic. And the fact that at both levels of model, I can build a toroidal hole into the structure indicates that this is probably a general property, that every second level model will have this Chevy Chase roundabout here, such that when the toroidal hole, which is really that is a signal, which is a toroidal hole at this level, will come in, it'll divert either this way or it'll divert this way. And this changes and possibly simplifies the discussion of how signals interact with each other at nodes at this level of model. Of course, what we haven't said yet is that once you have a model like this for second level, well, this model will work perfectly good for nth level. That is, all the way down in the recursion, we'll be able to use this thing as a prototype for the banded pipe interaction in the same way that we'll be able to use this model here as the prototype for the nth level of recursion for the vertical pipe structures. So this is a huge transformation in the way that I think about the second to nth level models of the triangular neighborhood networks. So immediately after building the 6-node second level model for both the banded pipe and the vertical pipe structures, I took the nodes, the models that I had built for second level for 5-edge nodes. And so this is the banded pipe, the banded pipe as shown by this green band of 3 edges. I had built this model, and it had a dome like this, that an inversion here in the bottom. That wasn't it was very weak, like the other one that I showed you. And so, although I didn't record this before, this model has the appropriate angles for the legs, if you want to call it, the pipes that go away from the node. So the model is angularly correct, and that's very interesting. So now I've put a 6-hole, actually no, it's a 5-hole. 1, 2, 3, 4, 5-hole, yes. It's a 5-hole toroidal hole. So now here is the vertical pipe version of the second level model for the 5-edge node. As you see in the green edges, this is a vertical pipe. It has a circumference of 6, and like the banded pipe version for the 5-edge node, this one was weak. It had a dome-like structure here, and so I've put a 5 circumference toroidal hole into this model, and once again you see the structure is absolutely perfect. It has the right angles, and so this structure is really quite successful. More to the point is that both models of the 5-edge node have 5 circumference toroidal holes in their center that stabilize the structure and make it useful. Again, the Chevy Chase circle is in the middle, and so at this level of model, signals that are toroidal holes would come along and come to the 5-edge node interaction, and they would be diverted either to the right or to the left, and this would be true in either model. Of course, these are just 0 scalings of these models. We could scale up once or twice or n times, and so the importance of these models is that not only do the 6-edge nodes have 2 versions that have the Chevy Chase circles in them, but these 5-edge nodes at second level have the Chevy Chase circles and roundabouts. And so now the question is, does every node have the same features, this toroidal hole in the center? And that's the interesting question that I'll address in the next sections. I've said several times now, I guess, that each level of model shows you certain properties. So here's the simplest view of the 4-edge node. It has a certain concavity to it that's quite clear. I'll show you the 4 field here. We'll use this model later on in one of the other videos. But the main feature you can see from this is that there's a rather extreme concavity, and that the angles that was apparent in the first level model, the angles for the emergence of the edges from the node are really very clear. And so I went to build a second level model for the 4-edge node, and it looks like this. I think of this as sort of a dachshund, if you want. The angles, this is a banded pipe version. The angles, the banded pipe is indicated by the green edges, the circumference 3. But you see, these legs here don't go out at quite the right angle. They should be going out at an angle like this. I mean, this angle here is okay, but this angle here in this particular model isn't quite correct. And of course, I could put a triangular hole in this face here, but there's really not enough structure in this particular model. And of course, we could scale this model, but that's a different issue then. But basically, still the angles were wrong. So I abandoned that model and came up with this model here, which is the vertical pipe. See, this is the indicator for the vertical pipes, and this is an 8 circumference pipe, and it has a toroidal hole, a Chevy Chase roundabout in it, and but it's still very much like this model, in the sense that the angles are not quite correct. Of course, it may very well be that that the 4-edge node has some variation in structure, and that there may be situations where exactly this set of angles between these legs and these legs is useful and necessary, one could argue. But of course, this model is successful in the sense that without it, it's very much like this model here, where there's no structure. But now, with the introduction of the toroidal hole here, this model is quite successful in terms of its structural stability, and of course then signals coming to this node, the 4-edge node, over the vertical pipes would then be diverted either right or left. And again, that is rather interesting. So the question is, can I make a model for the banded pipes? The banded pipe is indicated here by the green edges. It's a 3 circumference pipe. The toroidal hole has been placed in the center. This model also had not a weakness, but just an ordinary flexibility to it. The toroidal hole is put in the middle of this model. It too is perfectly stable. So the angles on this model are just perfect. They compare very favorably with the 4-field that we saw before. So once again, we have two models for the 4-edge pipe. We have the banded model, and we have the vertical pipe model. And this answers the question very nicely for the 4-edge nodes, so that we have 6, 5, and 4-edge nodes that work perfectly, and 3-edge, because we've seen 3-edge models also. Here's the simplest model of the 7-edge node. This model itself indicates a certain flexibility in terms of curvature. Remember, the 3-edge, 4-edge, and 5-edge are negative curvature. The 6-edge is neutral curvature, and the 7-edge is the first of the positive curvature nodes. Each level of model introduces more structure. So here's the 7-field shown in green, with the 7-edge node in the center, and then the purple indicating the spines of the structure. So I tried to build a second-level model of the 7-edge node. This is the banded model, as indicated by the green edges. That's a 3 circumference model. This model is not clear whether it's successful or not. The 7-edge nodes are used for forming toroidal holes. And very often you have 4 edges going in one direction and 3 edges going in another direction. I'd say, like with the 4-edge node, I'd say that the angles on these edges here are not quite correct. They really want to be something like this, and the model just doesn't want to do that. So I finished this model and I got closure. There are some 5-edge nodes here, some here, one over here, 3 or 4 over here. But and there's a 7-edge node in the center. But of course there's no 7-edge node on the other side. So, and I don't know how you'd make a 7 pipe and then fit the edges of the 7 pipe to a toroidal hole to a model like this. So this model is relatively unsuccessful. I mean, I just never was happy. Now, I think what I've seen in building these second-level models is that you have to search for larger and larger structures until you find the right configuration. So this is just an unsuccessful attempt to build a model for the second level of a 7-edge node. In the same way, you know that we've been doing banded pipe and vertical pipe models. Here is a vertical pipe model for a 7-edge node, and I've been able to stick a 7-edge pipe, a circumference pipe. You can see how this is much bigger than the 6 or the 3 that we've used in the past. And here the angles for the 7-edge node are, you know, one could argue approximately correct. I mean, they're all up like this, which is not correct. But, oh, I see, that's actually probably the answer. Why? You see, I haven't been able to figure how to interface. I mean, I started here, how to interface a 7 pipe with 14 edges that form the thing. There's just no symmetry that I can use to close this structure off. And so far, the attempts that I've made to make a 7-edge model, a second-level model for a 7-edge node in either the banded or in the vertical pipe styles, have been unsuccessful. And so I'll have to spend some more time now playing with the 7-edge node in an attempt to build both the banded pipe and the vertical pipe models. So the question really is, I of course think that I can build such a model, and it's only a question of finding the right symmetries, and that's a difficult conceptual problem always. But of course, in some sense, the whole notion of second-level models to nth-level models, the recursion, hinges on whether I can build this for 7 and 8 and 9 edge nodes. So this is the balance point that I'm at right now. Certainly, having built models, second-level models for 3, 4, 5, 6, is very successful. There's no question about that. Those models stand, and I feel very happy about those constructions. The 7-edge model, as I say, I've not yet found a solution, and I'll search some more. I don't quite want to be in a position that says, well, you know, if you don't get 7, then the whole thing is meaningless. I can't subscribe to that notion, but of course it is a reality.